Hello everyone, this is lecture 27 of Petroleum Reservoir Geomechanics, PTRE 465531. We will proceed today with module 3, where we left off. Before we start, small announcement. I think I will make it an official announcement on Blackboard, but the ladies in the administration emailed me that my request to make the exam, the second exam, from 50 minutes to 75 minutes was approved. So even though we have 50-minute lectures, because everybody is online, I'm able to have the exam being 75 minutes long, the second exam, but I will still make the exam for 50 minutes. So you should be having time. In the exam, time won't be a factor, if you know what you're doing, of course. Yeah, so that's good news. Now, the only thing is that if you have already booked an appointment to have it in a testing center, you need to cancel the appointment and rebook so that they book you with the new sort of rules for that exam. It shouldn't be an issue, and the testing center will understand that, hey, I mean, because if you booked before, they book you under the rules that we had under that exam at that time. Now you need to do it again. So that's the only thing. But you're going to have 75 minutes for the exam, not 50. And the exam is certainly doable in 75 minutes. I guarantee you that. We were not far away from the ending of module 3, actually. It's just I want to have, there are some example problems coming up. Okay, bedding planes. Well, we did talk a little bit more about shear failure, and we talked about layering that is very common in rocks. It's a form of heterogeneity, layering, thin layers. We call them bedding planes. It's a form of, it's a weak plane, okay? It makes it easy for the rock to fail. And the best way to make it easy for the rock to fail is to have a bedding plane in the direction you expect it to fail based on the loads that you're applying. So in this case, let me go back a couple of slides. Okay, I have I'm loading the material, the code with sigma 1. And I have a confinement with sigma 3, okay? If I have shear failure because of sigma 1 and sigma 3, it will be that direction of C equals 60 that we mentioned earlier, okay? So if I want to help it fail in this way, is by having layers in that direction. Now, if I have layers in that direction, I basically have planes of weakness in that direction, in that favorable to fail direction. So it makes it very, very easy to sleep. I make it easier for the core to sleep. So probably, if I'm making if I'm running a laboratory test with layering in that direction, I'm gonna get very, very low strength estimations for shear failure or resistance to shear failure for this code. I'm gonna get smaller than what it really is. Several rocks, they have mica foliation, which is basically plates. It's mineral in the shape of plate. It's very, very flat and thin. And these are plates of weakness. The way those plates are held together is very, very weak. So it's very, very easy to make them slide over each other. Very, very easy. The sample is strongest when the orientation of weak plane is perpendicular to the expected failure plane. So if I'm expecting it to fail, say, if I'm even for tensile failure, if I have a Brazilian test, I'm loading it, and I'm expecting it to fail like this, right? In tension. Okay, if I have layers in this direction, I make it easy for it to fail. But if I have the layers in this direction, I make it harder for it to fail. Now for shear failure, it's the same thing, but it's a little bit different. Because I have the confinement sigma 3, and what I'm applying on top, sigma 1, okay. And I'm expecting it to fail something like this, 16 degrees. Now, if I have planes in this direction, it's a bad idea, okay? Because I make it easy for it to fail. But if I have planes in this direction as well, sorry, in this direction, it's also a bad idea because it can fail the other way too. So this perpendicular is not exactly universal. The best way, I think, you either, the way to make it harder to fail is either having planes like this, or having planes like this. And the bigger the angle difference between, I think they have all, this is 90 from 60, so it's 30, and the other way. It's about the same angle difference. It's 30 degrees difference from the preferential failure plane, as we call it. But they are both gonna get pretty much the same resistance. I think the vertical, yeah, I think it's gonna be about the same resistance. But yeah, if you have it in the direction that you expect it to fail, that's gonna be that's the easiest you can make it to fail. And we were doing that when I was in Texas. We were teaching undergrad geomechanics lab, and we had about 5 or 6 labs a semester for that class, associated with that class. We had a lab on Brazilian test, a lab on UCS test, a lab on CS test, like confining stress test, what else? Some others as well. And they were giving us intentionally samples that had layering in them. And if you put them a certain way, you get a certain result that is different from if you put it a different way. And we were groups, and each of us were doing basically a core sample with different bedding plane than others. So we were getting different results, but it was expected to get different results. And the other thing you do, if you are the TA, because we have to put them in the oven before you give them to the students. And if you don't tell them that the core is hot, when you put it on their table, somebody moves to catch it, to catch it. And you need to remember to tell them that it's hot, otherwise they might, it's not that hot, but we put it in the oven before we run the test so that it's completely dry and doesn't have any saturation inside, any fluids inside. A similar phenomenon applies to tensile strength. Planes of weakness can greatly reduce tensile strength, applied in the direction of perpendicular to those planes of weakness. This is what I showed with the Brazilian test. Oops, sorry. Yeah, I showed it first and then I talked about it. Did you know that tensile failure can also be demonstrated on a more circle diagram? And this is a hypothetical, not a hypothetical, this is a rhetoric, so not a rhetoric question. It's a question that there is an answer. Yes, you can do it on a more circle diagram. We don't do that in this class, but it was basically to highlight something that I already said earlier on, that both polygon and more circle diagram can be used to show tensile failure. And we do that for the polygon case, we do that a lot in the research. And you will see that in the next class, first or second homework, that it is possible. Also, yeah, in the more circle diagram, you can show tensile failure basically by looking at the negative axis. Normal stress. How? Sigma 3, sigma 1. But we don't do that in this class because it's like we could have explored it, but I was like, let me show, because when you tell to somebody more circle, they immediately think of more Coulomb shear failure criterion. And it's true. Same thing with the polygon, but just wanted to show you that you can show everything in those plots. And the rhetoric question, a question that I don't have the answer, is something that we have been talking in the last 2 lectures, maybe 3 lectures, about, okay, how do you show these failures on this diagram? That's something I want to be interested in. And we have asked Lumster, and he was interested in too. How can you show these failures in this diagram? I know that we show the frictional limits, of course, but how can we show more stuff? How can we use this diagram basically for different, to indicate different rock behavior? Okay, I think there is an example problem coming up. Example problem number 3. A given site onshore is known to be subjected to a normal faulting stress regime and hydrostatic pore pressure. Calculate the SH mean at a depth of 5,000 feet true vertical depth, assuming frictional equilibrium of faults, critically stressed faulting hypothesis, basically, and a friction angle phi of 30. Okay, notice I gave you angle phi. I didn't give you angle psi. Didn't give you mu. Okay. We have critical faulting stress hypothesis, but I gave you phi, and from phi I want you to get mu. Okay. I know it's a normal faulting stress state, so SH means sigma S3. Okay. I know it's onshore, so okay. First, let's find, wait a minute, let me write something first. Ultimately, what I'm going after is this equation. Let me show you. Before I show you the solution, S1 minus PP, S3 minus PP is equal to this expression here that we learned before, which is a function of mu, right? Okay. Let me mathematically write it better. This is, what was it? Mu plus square root 1 plus mu square, something like that. Okay. So I have three unknowns, okay? I have hydrostatic pressure, pore pressure. So I know it's hydrostatic. That means 0.433 psi per foot. I'm looking for SH mean, which I know is this, S3. This is what I'm looking for. S1, I don't know it, but I think I should because it tells me it's onshore and I know the depth. So if I assume 1 psi per foot over Bertin, I can get S1. So I'm looking for S3, I have S1, I have PP, and I want to get mu. How do I get mu? From P. Okay. This is what I'm going after. Remember, I told you this equation is the most important equation for this exam. Okay? So mu is equals tan of F. So phi is arctan of mu. I reverse that and I have mu is tan of F. I gave tan of 30, 0.57, makes sense. Good value, 0.6 basically. And then I use this equation that I mentioned before. And for mu, 0.57, the right-hand side is no longer 3.12, as it is for mu equals 0.6. It's 2.993, basically. Okay? And now I proceed by, okay, I replace SV, which is S1 with SV because it's normal faulting, and S3 with SHB because it's normal faulting. Now, here is the catch. Pore pressure is hydrostatic, so 0.433 times the true vertical depth. And then the side is onshore. So given lack of other information, I assume that SV is 1 psi per foot. That's the lithostatic stress gradient from our first module. So 1 times 5,000 minus 0.433 times 5,000, that's basically S1 minus PP. And then at the bottom, I have SH min minus 0.433 times 5,000. I basically have one equation, one unknown, which I can very easily solve to 3,110. Now, let me tell you something. Before I do that, let me write here to make it clear. Normal faulting, so S1 is SV, S3 is SHB. Okay? Remember this. Remember this. That's how I got it. Maybe I need to state it clearly. But now this value of SHB, is it an upper bound or a lower bound? And here I say it's a lower bound. I need to ask you, why is it a lower bound? This is important. It's important for the exam. This is because if I look at this equation here, imagine I use a lower SHB. What will happen on the left-hand side? If I use a lower SHB, the left-hand, if, let me draw it, if this is lowered, the whole left-hand side increases, and it becomes unstable. So this SHB that I calculated using that equation is the lowest possible SHB at which my stress state remains stable. That's why I say lower bound. 3,109.9 psi would make this equation give me unstable to shear failure. Of course, it's going to be a small instability. I don't think 0.1 psi will make a difference. But from Luster's words in our lecture, in our seminar, maybe 3 weeks ago, 4 weeks ago, I don't remember, more than that. He literally said the order of differences, this delta PP difference that makes the faults to slip, he said in the order of bicycle tire pressures. He said 150 psi can make a difference. I was surprised too to hear it. I mean, that small difference is enough to make the fault slip at certain stage. And that is on top of the critical faulting stress hypothesis, basically. Talking in the real world. Yeah. So 3,110 psi is as low as SH mean can be. Okay. Now, a given site onshore is known to be subjected to a reverse faulting stress regime. Reverse faulting. Hard pressure is detected at 2,000 feet to vertical depth with PP equals 0.82 SV. Calculate the SH max at this given depth, assuming frictional equilibrium of faults and a fault and frictional angle of P equals 30. Now, same equation, same mu. So the right-hand side of the equation remains the same. I don't need to change anything, 2.998. But what about the left-hand side? What is S1 now? I have reverse faulting. Reverse faulting, very important. So I have SH max bigger than SH mean, which is bigger than SV. So what happens? S1 is SH max. S3 is SV, which I know because it's, I assume 1 psi per foot. So S3 is known now. S1 is unknown. And the pore pressure is known, but it's no longer hydrostatic. Is 0.82 times SV. So if I know SV, I know PP as well. Because from one I get the other. If I get SV from 1 psi per foot, I multiply that by 0.82 to get the PP. So again, I leave the equation. I reduce the equation to one unknown, one equation that I can solve. Very easy. Okay, so let me do it. I have SH max minus 0.82 times 2000. 82.82 times 2000, that's the pore pressure. And then I have SH max, which is my real unknown, and then SV. SV, I don't know it yet, but I can very easily find it. 1 psi per foot times 2000, or 2000 basically psi. And if I do it and I solve it, and I made a mistake here, which I need to fix. Enable editing. Very important mistake. SH max is 2720. This is a very important. These two examples are very important for the exam. Okay, I want you to understand them very well, how to do it. Backwards and forwards. That's what I was saying. You need to know how to use this equation. If you know this equation, how to use it, you're gonna do well in this. SH max. And now a question, okay, is it upper limit or is it lower limit? Okay, I have this unknown here, SH max. Let's assume that this SH max increases. What will happen to the left-hand side? It will increase. And it will become bigger than the right-hand side, so unstable. If I make this smaller, the whole left-hand side will decrease, and it will become more stable. It's less than the right-hand side. So this represents an upper bound of SH max. If I go higher than that, I have instability. If I get lower than that, I'm okay. So this is an upper bound. Remember from module 1, we talked about how you estimate SV. We talked about how you estimate SHV. And with SH max, we said it's very challenging. Okay, and there is a lot of studies about that because it's a case-by-case basis. Like in Australia, where there is reverse faulting stress states, and New Zealand, they use drilling-induced fractures, drilling-induced tensile fractures from image loss to get an upper bound and a lower bound for SHB, for SH max. In other places, we use a different equation. In Texas, we use another equation to estimate SH max because it's normal faulting. It's a case-by-case basis. In Australia, for instance, which is harder, you have to use image logs, etc. In some places, just calculating SH max, they write a scientific paper about calculating SH max in a specific location. It can be that difficult. It needs sort of it's like solving a Sudoku puzzle. You are worried about vertical and horizontal rows and columns at the same time, in a sense. It's like, it's challenging, it's challenging. Okay, problem number 5. Find the shear and normal effective stress on a fault plane within the following state of stress conditions. I have 23 MPa. Now I have MPAs, right? 20 MPa, I need to fix that for SH max. 13.8 MPa for PP, and my deep angle is 60. Okay. Let me make this piece. I'm gonna fix those slides. And so wait a minute. I'm given SV, I'm given SH max, SHB, pore pressure, E, and I've asked calculate tau and sigma N. That's very easy actually, because I was already given their equations. This is a very easy example problem. It's not as important as example problem number 3 and 4, but it's good just to apply your knowledge on some equations. I wanted to show you these equations because these are the equations behind that S1 minus PP divided by S3 minus PP equation. So this is how you calculate tau. This is how you do it. So sigma 1 is basically, oh, I need to ask myself, okay, it didn't tell me if I have normal or strike slip or reverse, because it's very easy to understand that SV is bigger than SH max, which is bigger than SH mid. So I have normal faulting stress state. So sigma 1 is basically sigma V. And my sigma, yeah, so this is basically sigma V, which is SV minus PP. And this is sigma H mean, which is basically SH mean minus PP. Okay. And I think I know the rest. 13 minus 3.8, because don't forget to subtract the pore pressure. And yeah, I need to fix those typos I made in the previous slides. I get 4 MPa. Okay, 4 MPa. What about sigma NN? Okay, it's a little bit of a more complicated equation, but again, I know C, I know sigma 1, I know sigma 3. I just plug in the numbers and I get what? I get 6.1. 6.1. And then, good question. Now, will I sleep or not sleep? Assuming it's a if you read the problem, it doesn't say specifically, but let's assume it's a fault plane. So I already have a fault. So I can very much assume that the model is pre-fractured. The rock sample that I'm dealing with is pre-fractured, okay? Because I already have a fault plane. Pre-fractured. So tau naught equal to 0. I already have fault in the direction that it will most likely slip. And we said my tau is 4 MPa, and my normal stress, this is tau, and my normal stress was it 6.1? I think sigma n 6.1. Some people use 2 n's, or my n looks like an h actually. Sigma n. Okay. So if I have that, I need to know, will it sleep or not sleep? The equation to do that is basically this. Tau equals mu sigma n. And this is the same equation as this. As 1 minus pp, as 3 minus pp, equals, what was it, mu plus 1 plus square root of mu squared. It's the same equation. It's the same equation. It should give you the same results if you do it properly. So I go to the next slide to see my results. And it didn't tell us what is mu, but we can calculate a critical mu, okay? So basically, if my mu, because I have tau equals mu sigma n, okay. To make sure, let me show you. For stability, I need this, okay? So if I do tau over sigma n equals to mu. If my mu is bigger than this ratio, I have shear slippage along the fault. If not, I don't. So let's calculate it. So what is the critical mu? Is basically 4 divided by 6.1, which is, hey Siri, what is 4 divided by 6.1?
It's approximately 0.6557.
Okay, Siri says, thank you, Siri.
Of course.
6557. Okay. So that's a logical value. K is within the range Okay, we found like 0.57 is not completely out of range, but we said around 0.6 to 0.8-ish and 6-ish. You can go a little bit lower, but don't go too low. If I'm above this, if I'm above this, I'm gonna have wait, I forgot how to. Let's see. So if this is too high than this, we have slippage. So basically the higher, if I go, if my mu is above this value, this 65.5, basically mu upper is 0.6557. That means if I'm 0.6, I'm good. If I'm 0.65, I'm good. If I'm 0.6556, I'm still good. Above that, above that, I have a problem. Right? So if I have, because 4 is 0.6557 times 6.1. Okay. What if I have lower? It means that, so I need to compare those values, okay? So for this mu, this is equal to mu times this. Okay, for a lower value than for a 0.6, let's say, it is 0.6, tau will be bigger than for a smaller value, tau will be bigger than this if mu is smaller than 0.6. So I will have instability. I have instability at the lower value. So I was wrong when I said upper. It's a lower bound. I apologize for that. Lower bound. Okay. So if I'm above, if I'm 0.7, 0.8, I'm good. If I'm and remember, higher mu makes the polygon bigger. If I'm lower, I have a problem. So I need my mu to be higher than this critical value I calculated, which is the lower bound, represents the lower bound. Okay, so that brings us to the end of module 3. I told you, I will say even problem 5 is important, especially problem 3 and 4, also 5. I want you to understand how those work. Because as we said, this equation is by far the most important thing you learn in this module. Which is the same as basically this equation. And I want you to know how to use this stuff backwards and forwards. Any questions on the homework? No questions? Okay, so what did we learn in module 3? We learned about fracture modes and rock failure types. We learned about tensile failure and the Brazilian test, or we learned more about tensile failure and the Brazilian test. We talked about shear compressive failure, unconfined and confined compressive strength test that we can very easily run in the lab, quick test. stress polygon and more Coulomb diagrams. We also learned about, we did spend time on, basically, we can say here, Lundstern and Zoback 2022 plots, but those, they show the same thing, which is basically frictional limits, which is basically the limits to shear compressive failure of pre-existing faults. And something very important that we learned, and I should have put it, and I didn't, I should have. I will put it as number 7, but should be higher up, is the critical faulting stress hypothesis. If you go to the class textbook of Zoback and you try to search in it, the control, if you have the electronic version, Control F and write hypothesis. And it's going to show you the critical faulting stress hypothesis. Very, very, very important. And that brings the end of module 3. Hope you enjoyed it. Oh yeah, pre-existing faults. Yeah, I already had it, sorry. The second screen shows me what is the next thing after I press animation, but sometimes it jumps. It shows me 2 things later for some reason. It's not very sensitive. It didn't show me this. It was showing me the last slide, which is basically the reference, which is, I was going to say, oh, that's the book I'm talking about. But it had another point that I had missed. Anyway, so maybe I go in, now that we finish the module, and we are very well with time. I will go through the slide deck and fix everything that needs to be fixed. There are some important stuff like, okay, MPA needs to be fixed. Here is, it was SHB, it said SHB, but it made SH max. Some other stuff here and there. And yeah, I mean, I will try to make the slide deck better ahead of the exam. And we do have time until the exam, because the exam is on the 15th of November, is 2 weeks from today. So we have 2 more lectures in the module 4. The next lecture, I'm gonna make it half on module 3, just the main stuff, because it's an important one, and maybe start the module 4. Well, the module 4 stuff would be more than the module 3. And yeah, after that, 2 more module 4 lectures, and then review. If you have any questions on the homework, please bring them over to me either in the office hours or by email. And the TA, we cannot give you the answers, but we can help guide you to the right direction. As I say, I tell Kalu the same thing. Don't get disappointed about your grades on exam 1. There is plenty of chance to fix everything in exam 2, but you need to know what is going on. You can go, don't expect that it's going to be an easy test, because the first one you did not do well as a class, I guess. But it's going to be challenging as well. But now you know what to expect. Let's put it this way. So you need to be calm, go there, take as many points as possible. Don't leave anything on the table. Thank you very much. Have a nice weekend. I will see you all on Monday. Thank you very much. Oh yeah, and the Monday before the exam, of the week of the exam. I don't think there is a class that day. So it's basically 1 or 2 lectures. We can do basically 1.5 lecture on module 4, and then we will start reviewing ahead of the second exam. So yeah, maybe the next lecture will be almost completely on module 4. Thank you very much. Have a nice rest of your day.